Have you ever wondered how a company like Netflix knows what you want to watch next? Or how an airline predicts flight prices? Well, it's not a crystal ball. It's actually some really cool math called time series analysis. And today, we're going to dive into how we can use the patterns of the past to get a pretty good glimpse of the future.
All right, so here's our game plan. We're going to build this whole thing from the ground up, step by step. We'll start by figuring out how to even read the patterns in our data. Then, we'll put together our first forecasting model, and then we're going to upgrade it into a seriously powerful tool that can handle the messy, complex data you find in the real world. By the end, you'll see the whole picture.
Okay, first things first. Before we can even think about predicting anything, we have to learn the language our data is speaking. We've got to break it down and understand its fundamental ingredients. So, to make this real, let's frame this whole thing with an example we can all get our heads around. Imagine we own a small coffee shop. We've got years of sales data. How in the world do we take those past numbers and make a smart guess about what we're going to sell next month?
The raw material we're working with here is called time series data. And honestly, it's a simple idea. It's just a set of numbers recorded in chronological order. That's it. Our monthly coffee sales, that's a perfect time series.
So the very first pattern we're going to hunt for is a trend. Pretty straightforward, right? Is the data generally heading up, or is it heading down over the long haul? For our coffee shop, hopefully we're seeing that nice, slow, steady growth as more people discover our awesome coffee.
Next up, we have seasonality. These are those predictable, repeating patterns or cycles that happen at regular times. And for our coffee shop, the pumpkin spice latte is the perfect example, right? Every single fall, like clockwork, sales get a big boost. That reliable spike is seasonality.
Okay, now this next one is super important. It's a concept called stationarity. All this means is that the basic properties of the data, like its average or how spread out it is, don't change over time. You see, our forecasting models absolutely need this stability. Trying to predict something when its average is always changing is, well, it's like trying to hit a moving target in the dark. It's just not going to work well.
All right, so we get the basic ingredients of our data. Now let's cook up our very first recipe for forecasting. This one's called the ARMA model, and it's designed specifically for that nice, stable, stationary data we were just talking about.
So the ARA model has two key parts. On one hand, you have the autoregressive, or AR part. This is all about momentum. The logic is simple. If our coffee shop had high sales yesterday, there's a good chance sales will be high again today. On the other hand, you have the moving average, or MA part. Now this one's different. This is the part of the model that learns from its own past mistakes. If our model predicted too high yesterday, the MA component helps pull today's forecast down a bit to correct for it.
Okay, so we've got our AR and MA components. But how much of each should we add to our model's recipe? A little bit of AR and a lot of MA? We can't just guess. We need to put on our detective hats and look for some clues hidden in the data itself.
And our two main detective tools are these special plots called the ACF and the PACF. The autocorrelation function, the ACF, basically shows us how today's sales are related to yesterday's sales, the day before that, and so on. The partial autocorrelation function, or PACF, is a little more clever. It measures the direct relationship. It's like asking, how much did just yesterday's sales affect today's without any of the ripple effects from days before? By looking at these two plots, we can figure out the exact amounts of P and Q, our AR and MA ingredients that we need.
This is all making sense, but there's a pretty big catch. Remember how we said the ARMA model needs that stable, stationary data? Well, what about our growing coffee shop? We already said it has an upward trend. So what do we do when our real-world data isn't so well-behaved?
And that is the challenge. That lovely upward trend in sales that we're so proud of, it means our average sale amount is constantly increasing. It's non-stationary. If we throw an ARMA model at this, it's just going to get totally confused because the baseline it's trying to predict is always shifting.
So, what's the solution? Well, it's this incredibly elegant and surprisingly simple trick called differencing. Instead of looking at the total sales number each day, you just subtract yesterday's sales from today's sales. That's it. By doing that, you're now looking at the day-to-day change. And just like that, poof, the trend is gone, the data becomes stationary. It's a brilliant little fix.
All right, this is the moment it all comes together. We've talked about the AR and MA components, and now we know this cool differencing trick to handle trends. So let's combine all of it into one super-powered, all-in-one forecasting tool.
And here it is, the ARIMA model. The name itself basically tells you the instruction manual.
The I right in the middle stands for integrated. That's our differencing step. The D just tells us how many times we had to do it. Then, once the data is stable, we apply our good old R for autoregressive and MA for moving average components. It combines everything we've learned into one logical, powerful process.
So we have our ultimate model. We have the tool. Now, what's the actual workflow for putting it to work and finally getting that forecast for our coffee shop?
It really boils down to a three-step process. Step 1, identification. We use our detective tools, the ACF and PACF plots, to find the right numbers for P, D, and Q. Step 2, estimation. This is where the computer does the heavy lifting, using some fancy stats to calculate the perfect settings for our model. And finally, Step 3, diagnostics. This is crucial. We look at the model's errors. If the errors are just random noise, that's a fantastic sign that our model captured the real patterns.
And as part of that final checkup, we do one last quality control step. Think of it like a meticulous inspector on an assembly line. A statistical check goes through every single piece of our model and asks, hey, are you actually doing useful work here? Are you helping predict the future? This makes sure there's no dead weight and that our model is lean, mean, and effective.
And with that, after identifying the patterns, building the right model, and validating all of its parts, we are finally ready. We can press the Go button and generate a real, statistically sound forecast for our coffee shop's future sales.
So think about what we just did. We went from just a messy pile of past data to a powerful prediction engine. We decoded trends, we built the ARMA recipe, and we upgraded it to the ARIMA model to handle real-world challenges. You now have the fundamental building blocks of forecasting. So the only question left is, what future would you want to predict?